So anyway, in this one you have to do both the, you have to calculate the work done on the box. And the work done on the box is easy. It's just the force of 505 times the distance that it travels and the angle, the cosine of the angle, which in this case is 20 degrees, right? But for him moving himself up the ramp, you have to use a little bit of math that we've done before, or consider it, I suppose, geometry that we've done before. And so this is how you would do this. You have your incline here, you have the 20-degree angle, whatever it is for you, and his weight, the weight of the person who's pushing here, you know, his weight comes down this way, remember? But we want to know what component of the weight is pushing him down the hill this way, because that's the one he has to overcome for this distance. So what portion of that weight is pushing that way? Well, remember when you rotate your axes, you have your axes like this, right? And you have a component that goes this way and a component that goes this way. And this is your angle theta. So if this is my weight W right here, the one I'm interested in is this one, which is opposite the angle theta, which is going to be equal to W times the sine of theta. So that is the force of the weight that is parallel to the surface here. And so that one times the distance is going to give you the work that he has to do to overcome his own his weight to get up that. So it's going to be W sine theta times the distance times the cosine of theta, which is the theta in this case is going to be 180 degrees, right? Well, yeah, and it's actually 180 degrees for both of them. So the amount of, so you end up adding those two together because he's pushing the box up and he's pushing his body up. So you add those two together. This one, if you use this, here you're going to use the angle 20 degrees, and with the cosine theta, it's going to be technically 180, but so will the other one, so they'll both be negatives. You'll add them together, and you'll actually just make them positive because they want to know the work done on the kratom on his body to get up the ramp, which is pushing them. They're both going the same direction. So he's actually pushing this way. So actually, I guess that wasn't. So the force that he exerts on his body is actually this way, so that's not going to be 180. That's the force he exerts is against the weight. The weight is pushing down, but he's pushing against the weight. So he has the force that he pushes on his own body with, that's this way, and then he has the force that he pushes on the box with. That should make this one the force counteracting the weight, and this one force pushing on the body. And then you calculate the work from each of those and add them together, and you will get. So that one's just a little more complicated, not terribly difficult, but just a little more complicated. Here is how much work is done against the gravitational force. Whenever you see a problem that says work done against something, that means that the work is being done in the opposite direction of that. So gravitational force is straight down, so they want to know how much work is being done straight up. Now, if you're talking about work as you're sliding up a hill or going upstairs, you have to take the angle of the hill or the angle of the stairs into account, because there's work both going up and sideways when you're going upstairs or a hill. But if they're just saying the work done against gravity, they only want to know how much work you did in the upward direction, which is against gravity. So all you need to know here is the vertical distance, which they tell you. Here's the vertical distance, 380 meters. And then you also need to know the weight of the briefcase, because that's the force you have to overcome. Now, I think that it'd be better to say what is the minimum amount of work to do this, because if you actually move at a non-constant speed, then you will actually do more work. So what you're calculating here is actually the minimum amount of work, but I can't really change that. So anyway, this is the mass, so you multiply the mass times gravity 9.8. Well, I guess if they say how much work you do against gravity, this is still the way you do this, because if you're accelerating the briefcase and not going at a constant speed, that acceleration is not necessarily done against gravity. That's the work that you do to accelerate. So I guess the way they worded it is fine. But all you need to do when they say against gravity is find the weight of the object, which is the force you have to exert to overcome gravity, and then you multiply by the distance that you travel straight up, and you're good to go. You don't even have to use the cosine theta, because the cosine theta is going to equal 1, and you're done. So this is another one where it's very simple to calculate. And the only reason I give you all these different ones that use the same simple calculation is I want you to see how that simple calculation works in many different instances. Now this one is a little bit different, because this one is that same simple calculation, but it's not obvious that it is that. Here they tell you the force is shown in the figure below. So here is a force on the y-axis and the distance on the x-axis, and it's only one-dimensional. So the work being done is going to be equal to force times distance, which actually, graphically speaking, is the area under this curve. So you just need to calculate the area under this curve. How are you going to calculate the area under this curve? Well, you're going to go ahead and break the curve up into triangles and rectangles. Cut right down this way. You know, you maybe use a ruler to see where it hits here. It looks like it's hitting at about 2. And then do another one on this side to see where it hits, and see what the height of these triangles are and the base of these triangles are. Height times base times 1/2 is equal to the area of that triangle. And then you take the area of the rectangle in the middle and add all those areas together. Once you've added all that area together, you know the total work being done. They actually want to know from different places to different places. So from 0 to 2, they want to know this little area of this triangle. And they want to know from 2 to 12, which happens to be the area of this rectangle. And then they want to know from 12 to 14, and then the whole thing. So they have you do it one piece at a time already, which just makes it even easier, right? But this is always true if you plot the force in one dimension over with the distance in that same dimension. This is the force in the x dimension. This is the distance in the x dimension. If you plot the force against the distance, you will get a curve, and the area under that curve, and it can be a curve for real. It doesn't have to be like a sharp-edged curve. It can actually be some kind of weird curve, and that will tell you the work that was done. In fact, you can even do this. You can even plot this out so that you actually get a closed curve. You can actually come back in distance and at a different force, and actually come back to this point right here. In which case, the work being done would actually be the area enclosed by the curve, because you would subtract off the little piece down here. And in the next problem, you can actually see that you can actually do work that is negative here. Here they do negative work because it's below the x-axis. So in this case, you add the area here and subtract the area here, and you get the total amount of work. So the second one here is actually a negative work being done. And here you're going to estimate using these boxes as your units, essentially. So you have 1, 2 units for the base, and then you have 3 units high. So it's 6 units by 1/2 gives you the area under this part of the curve. You do the same for this triangle, and then the same. You can do this whole triangle from A to B if you want, and then the whole triangle from B to C like they want. So that tends to be fairly straightforward. Now, did we talk about kinetic energy yet, or did we just talk about work? Just work? So the next parts are most about kinetic energy, and then the very last few are about, I guess we have a few about kinetic energy, a few about the energy theorem, and then a few about power, and then we're done. But most of the rest of these are not really heavy-duty calculations. There are some with the energy theorem that are longer calculations, but there's nothing as far as calculus goes really, or really any difficult vector calculations, because remember that energy is not about vectors. You get rid of the vector qualities when you deal with energy. We saw that with the work. So that's enough to get you started. You can get all the way through number, looks like you can get all the way through about number 8. So that's like number 4 through 8 without having to do anything really drastic.
So you just said when working with work, you get rid of vectors?
Yeah, because remember the work is equal to the force vector times the displacement vector using the dot product.
Which gives you scale.
When you use the dot product, you get a scalar. So that's always the first thing you want to try to get done is get that dot product done, so you're not dealing with vectors anymore. And since the dot product is inside of the integral when you're doing the calculus part, that's nice because you can do the dot product, pull all the constants out, and just do a normal kind of integral.
So how do you? I'll ask you later.
Yeah, we will cover that. We will go over those difficult ones here at the end of class or tomorrow at the latest. We'll get you through those. And the purpose of those more difficult problems with the calculus is not necessarily to make your life miserable. It's to show you that work is much more than we say it is. Is really what it is. We're not going to deal a lot with the three-dimensional or two-dimensional work functions at all. But we do want you to know about them. We want you to be aware of them. Because if you do go on in engineering, you will be taking a class where you will be doing that a lot. So you need to be familiar with it. You don't need to, you'll learn it again in that class. That class is called Dynamics. And you'll take it sometime in your junior year, most likely. But if you've never seen it before and you go into that class, you're going to be behind a little bit. You want to have seen it before at least a couple of times, just so that you're aware of what's happening and you can kind of jump into it more cleanly, which is why we teach it here. In physics, if you go into physics, you'll also take another class that is completely about that, and which is called mechanics. But anyway. All right, so that's kind of the first half of the homework there. Gets you through number 8. So let's go on to look at so essentially what we've just done is we've shown you this version of the work function, and then we've shown you this version of it where it kind of waters down into something very simple in a single dimension without having to deal with vectors, right? And this what you're always going to do, even if you have multiple dimensions and an integral to deal with, is you're going to work through that integral, get the dot product completed, and get the integral done so that you end up with something simpler like this that you can just plug numbers into. And that's kind of the whole idea there, even if you have to do some complex math. And I do understand that some of you have not taken Calc 2, so integrals are a little bit new to you, but you will get to integrals before the end of Calc 1, and you will start to become familiar with them, and it will make a little bit more sense at that point. But at this point in your education, it's mostly about just exposing you to these things so that when you see them, you start to make connections with them. So don't be too worried about it. Let's see, let's go to 7.2 and let's learn about kinetic energy. So the word kinetic in the Greek means movement, and so kinetic energy literally means movement energy. There is an energy associated with movement. Movement itself is energy. In fact, this was discovered in the 1800s, I would say. This was really starting to be understood, so not that long ago. We're talking maybe 150 years or so ago. There was a guy that was doing some research with pollen particles. So pollen particles are very, very tiny particles. They're some of the smallest particles that you can see with a normal microscope. Normal microscopes have limited power. They have limited ability to see things. And one of the smallest things that they can see are very tiny particles of pollen. And as well, of the microscopes back then. There are microscopes now that can do better. And then there are other microscopes, quote unquote, that are not really microscopes, like electron microscopes and so on and so forth. Those things are not actually microscopes per se, but they can see much smaller things. But anyway, this guy named Brown was studying these particles in a fluid under his microscope, And he noticed that they didn't just kind of sit still, they actually bounced around for some reason. And he couldn't figure out why they were bouncing around. And believe it or not, it was actually, let's see, was it? I think it was Einstein. I think it was Einstein that actually gave the explanation for Brownian motion. And I believe he did it in one of his papers in 1905. I'm trying to remember if that's actually true. Let's look it up. So this is called Brownian motion. Brownian, what he discovered was that that these particles move randomly. They kind of jerk around and bounce around, and it's not like they're not like hitting off of each other necessarily. It's just they automatically just kind of move in some random direction for some reason, some random speed, and he didn't really understand why. So this guy's name was Robert Brown. He was a botanist, and it was 1827 when he observed this, and he couldn't explain this. But when was it explained? Let's see. It doesn't say. I'm pretty sure it was Einstein. So let's just type that in. Yep. Yeah, so it was in 1905 actually, and in 1905, Einstein, easily the most brilliant physicist, but maybe even the most brilliant scientist, and possibly even the most brilliant human being who ever lived. It's very possible. He put his finger in just about everything and came out with just amazing results every time. But anyway, and most of that without actually even seeing what he was doing the science on. He usually didn't even do the experiments. He just figured out what was happening from other people's explanations of the observations. So anyway, the point is that Einstein was, of course, in 1905, he was reading papers by people like Robert Brown, and he was trying to figure out what the science was behind it, the explanation. And not only did he just want to explain it by just talking about it, he always wanted to have some kind of mathematical explanation, some mathematical proof, you could think of it as, that this would be correct. So what he actually did is he took Newtonian physics, Newton's physics, and he said, if Newton's physics is true for these particles, then the particles must be, there must be something running into the particles. There must be something hitting these particles. And what his suggestion was is that atoms were hitting the particles. That atoms in the fluid were hitting the particles. And the particles, and people have been studying this for a long time. One of the things they noticed with Brownian motion is that if you put the particles in a warmer fluid, the particles moved quicker. They had a faster movement. And Einstein was able to explain that as well. He was able to explain that using mathematics and saying the mathematics of movement and heat and all these things show that this is what will happen, and he was able to match that to the results. And that's part of the brilliance of Einstein. And believe it or not, before 1905, people weren't really understanding atoms all that well at that time. Atoms were not well understood. There was a lot of argument about what they were, what their structure was, why. I mean, even the periodic table was not complete, and it wasn't in the right order at that time because they didn't understand atoms. Chemists hadn't figured it out. Chemists never seen an atom or really done any experiments on atoms to really figure it out until Mendeleev came along. They tried, and they had a lot of different experiments that came close, but nobody had a real explanation for this when Einstein was doing this work. So this was a big deal. So kinetic energy is this energy, and along with other people's work from before Einstein and people that came after Einstein, this idea of kinetic energy really came to fruition, where we realized that movement and energy are related. Now there was another guy that did an experiment that also showed this, and it was a much less quantitative. It was much less mathematically rigorous, you could say, but it is just as valid. And this guy's name was Joule, and that's why we call the energy unit joules. Newton meters is joules. The experiment that he did is he had a big bucket of water, and it was completely surrounded by like really good insulation, and he had a really good thermometer in the water, and he had this handle that, well, actually, I'll just show you the apparatus because it's easier to just look at it. So Joule's apparatus looked like this. I want a big one. Is that a big one? Can't really tell. Why doesn't it just open the damn thing? James Prescott Joule. There we go, that's a nice big one. All right, so James Prescott Joule came up with this apparatus where he has, so these are the paddles inside the bucket of water that has all this insulation around it. Here's the very nice thermometer sitting in it. And then connected to the paddles was this kind of axle that was connected to this string that went over this pulley where this weight was hanging. And what he'd do is he would lift up this weight by winding the string around this axle. He'd lift it up to a certain height, and then he'd let the weight fall some certain distance. Now they were understanding things about potential energy at that time, and how potential energy could turn into kinetic energy. And of course, as this weight falls, it goes from potential into falling kinetic energy, because the weight is now moving as it falls. But if you just let the weight fall without being tied to the string, it goes faster. In other words, when it's tied to the string, there's a loss in kinetic energy here somewhere. And where does that kinetic energy go? Well, it goes into turning the paddles here. So there's some kinetic energy in the fluid now. The fluid is moving, the paddles are moving, and he was able to calculate the potential energy drop as the mass dropped from here to here. And he was able to calculate the potential energy of the moving pulley, the potential energy of the moving string, the kinetic energy of the moving pulley, the kinetic energy of the moving string, the kinetic energy of the rotating paddle and axle, and there was still some missing energy. And guess where that energy was? It was in the thermometer, right? The temperature went up when he did this experiment. The temperature of the water went up. Now it was just a little bit, but it was significant. And so what he was able to show is that moving liquid, or even moving fluid of any kind like air, has more energy in it than still liquid. And in fact, when you heat up a liquid, or you heat up a gas, or even if you heat up a solid, it actually moves. There's actually movement. But he didn't really understand how that movement displayed itself on a microscopic level. He didn't really understand atoms like Einstein did and others. So when Einstein came along and talked about Brownian motion, they started to think, well, maybe Joule's experiment and this Brownian experiment and Einstein's explanation are all connected, and they started to put together this idea that temperature is actually just a measure of the kinetic energy of the atoms in a fluid, or the atoms in a solid, or the atoms in a gas. So it's very important research that was done over centuries and put together in the 20th century, early 20th century. 1905 was a very good year for Einstein. He had 5 papers, and all 5 of them were amazing papers that he wrote. Nobody's ever had quite a year like that since. Okay, so kinetic energy then is this energy of movement, and it was actually, I think I mentioned this, that there was actually a woman who came up with the equation for this. Well, many people came up with the equation, but it was a woman who identified this equation. or this formula as an energy formula. Her name was Madame du Châtelet, Marie du Châtelet. So Madame Marie du Châtelet. And that was like in the 1700s, early 1700s. So that was really, really strange at that time because most women were not encouraged in science at that time. They were mostly discouraged from science. But she had brothers and a dad that really encouraged her. She was also. It also helped that she was very close and intimate with Voltaire at the time. Voltaire being a very liberal philosopher and very influential, he was able to get her the notoriety she deserved as well. So that's kind of interesting piece of sexual politics and history. But anyway, the kinetic energy is equal to, for an object moving at a constant speed, 1/2 mv squared, or a constant velocity. Actually, at a constant speed. But anyway, 1/2 mv squared, the mass of the particle times velocity squared, where that's the speed squared, not just the velocity squared. And you can have many particles that have speeds and masses, and you can add them together to get a total kinetic energy for an entire system, right? And it turns out that because our velocity is actually related to momentum, you can actually get another equation that is equal to the momentum squared over 2 times the mass. And this is the one that kind of confused people, that the kinetic energy and the momentum were kind of related because they weren't sure which one was which one was energy related and which one was momentum related. And momentum and energy are 2 very different things, but they are related to each other mathematically. So in this equation, you have a different version of that. It's the momentum squared, the magnitude of the momentum squared over 2 times the mass. In any case, you can see that the velocity is very important for energy. Kinetic energy is very, very dependent on velocity. If you double the velocity, you quadruple the kinetic energy. If you double the mass, you just double the kinetic energy. But if you double the velocity, you quadruple the kinetic energy. And this has a lot of importance, for example, when you're driving down the highway. If you're driving down the highway at 60 miles an hour and you crash, you do a fair amount of damage. But if you increase that speed just to 75 or 80, and then you square that number, the amount of damage you've done is directly related to the kinetic energy involved. And so you do a lot more damage just going a little bit faster, right? In fact, I think one of the biggest differences is between 15 and 25 miles an hour. At 15 miles an hour, very few people are ever killed in a car crash. Very few people. At 25, it happens actually fairly regularly. If you run into something that is stationary at 25 miles an hour and you're not wearing your seatbelt, you're not likely to survive at 25 miles an hour. 15, you can. But at 25, you're not likely to survive if you're not wearing your seatbelt. If you're wearing your seatbelt, you're good up to about 50, 60. Right? At 50 or 60 miles an hour, you're safe. And you get up to about 75 miles an hour, and it's iffy. If you have airbags, you can survive at 75 miles an hour, right? But at 80, 85, 90, it doesn't really matter what you're running into. You're not likely to survive an impact at 80 or 90 miles an hour, no matter what it is. Airbags or not. Airbags will kill you at 90 miles an hour. So that's an energy thing. And people just say, well, you need side airbags. No, it doesn't really make a difference. At 90 miles an hour, the amount of energy that is dissipated is just too much. It doesn't matter what dissipates it. It's just too much for the human brain, the human spine, and the human lungs, the human heart. I mean, you can stop your heart by an impact with an airbag. And if you stop your heart in a car accident with an airbag and paramedics aren't there in 5 minutes, you're dead. That's it. Unless somebody starts CPR, somebody starts emergency CPR right then and there, which you hope they would do, but not many people really know that. You hope you crash next to an EMT guy or an Eagle Scout or somebody who's been a lifeguard or something, or a nurse, but you don't always. Sometimes as soon as you call 911, they'll tell you to do that, but some people don't really know how to do it. So anyway, the point is that energy plays a huge role in car accidents. And so calculating the kinetic energy, you need to know the speed, you need to know the mass, and you can rearrange the equation any way you want. Here they do it for different frames of reference and so on and so forth. But there's not really much, we're not dealing with calculus with kinetic energy very much. So there is a calculus component to kinetic energy, but we don't deal with it in this book in great detail. It's just a little too much for this book, for this class. So we're done for today. Go ahead and get started. That should get you through in the homework. Let's see, in the homework, that should, chapter 7, that should get you through for kinetic energies. So you have a kinetic energy problem in number 9, 10, 11, and then in number 12 we're doing the energy theorem, which we'll study a little bit tomorrow. So we'll do the energy theorem tomorrow, and then we'll do some more homework. Help you out with some more homework tomorrow. Sound like a plan? What's the one you were working on?
Number 3. Chapters.
Which one is that one?
It's an article.
Oh, right. So this one is certainly a big challenge because of the calculus. I'm kind of trying to decide if I want to keep it in here. I kind of do want to keep it in here because this form of this equation is one that is used quite often. It's more often used in spherical coordinate systems. So second semester when we start doing charges that have this spherical field to them, or gravitational fields that have a spherical field. This is a very common form for a force function. So
Do I need to solve for y? Like I get y in terms of x?
So that is part of the problem. That is part of the problem that you'll have to do, because you don't want to have So you can do this a couple of different ways. You can actually do the integral in 2 dimensions using 2-dimensional calculus. You can do it that way. That can be done. Or you can solve it. You can solve this for x or y in a situation, and then plug it into itself. You essentially get a. So what you've got here is you've got 2 things. You've got the force function, and then you've got the displacement function. The displacement function is the thing that relates x to y in this problem. In this particular case, the displacement function is a straight line, and it has a particular slope. If you plot this out on a thing, you can figure out the equation for the line, and that will tell you the relationship between x and y. And then you can plug that into the force and get a function that's only in x or only in y. And then you can do the integral. Regardless of whether or not you do that, the integral is still pretty complex. And I had to actually, I didn't have the integral I couldn't find it in one of my integral books, and I don't know if it's available in the textbook, in the integral tables there, but it is available on this wonderful website that I'm going to introduce you to. And when students get to Calc 3, I usually introduce them to this website. I can't remember if I've introduced it to you before, but it's called Wolfram Alpha. Have you ever been to it? Wolfram Alpha is like a very powerful calculator that gets married to Google. So it's a search engine that's also a calculator. you can actually, I mean, you could actually cheat on your homework and plug in the question into there, and it'll pretty much do almost any question you can imagine. Okay, it's a very powerful mathematics and science engine that will actually search out theories and search out equations and plug numbers into the equations and give you an answer. So that's how powerful this can be. Now you can't really use it for that at that level unless you pay for the Pro version, and this is just the free version. So if you upgrade to Pro for like $100 and something a month or something like this, then yeah, you can do that. But you can still do a lot of stuff with this. So for example, we can do this integral. So if I do this, if I say that f equals, in this case, f equals x times I hat, and to do, I'm trying to remember how they do I hat. I think they just call it I hat. Let's check to see if that's true. Doesn't look like that's how they do it. So I'm going to do this f. So I'm going to do just the x. X divided by. Actually, I'm not even going to do this. I'm just going to do the integral. So here, this is how you type in the integral. You do int, and then you plug in x, and then I'm going to divide x by x squared plus y squared to the 3/2 power, like this. And you type it in just like you would in MATLAB. They use the same code. In fact, they use several versions of code, so you can type it in like you would in Fortran, and it would still recognize it. But if I type this in and I do this integral, oh, and I also have to tell it where I'm integrating. So here I'm going to integrate with respect to x. I think it assumed I was doing that, but I'm going to put a comma here with respect to x like this. And you can even put in limits. You could say x equals 0.5 pi or something, and it would actually do the integral. In this case, it's just going to do the open integral for me. So this is what the integral comes out as, and you can check to see here that this is correct, the correct integral. Right? I didn't put in the y part, the plus y part, but what it's assuming here is that it's assuming y is a constant here, and this is what you get out in the end. So this is what you would put, this is what you would evaluate between x and y. However, you do need to consider that y is dependent on x. So you have to go ahead and find that dependence and plug in x for, or y for x here and do the same thing in the numerator. But so you could do, yours would look more like, well, okay, first of all, what you should do is you should actually do the dot product first. The dot product. So the dot product between so your force vector is, remember your force vector looks like x I hat plus y j hat over this huge root thing, right? This 3/2 root thing, x squared plus y squared. That's what it looks like. So this vector, and then your r vector. Well, your r vector goes between 2 points. Whatever 2 points there are. It's this point and this point. And this point has, let's say this point is 2, 1, this point is 5, 3, or something like that, right? Yeah. So this is my vector. This is my starting point, this is my ending point, and it could be this way. Your starting point could be up here and ending point down here. Regardless, my vector goes from here to here, and the way that you build this vector is you take the end point in x and subtract the beginning point in x. 5 minus 2 is 3, and then 3 minus 1 is 2. Right? And so this one is actually 3I hat plus 2j hat. If this one went from 2, 2 to 3, 5, but your starting point was here and your ending point was here, this one would be 2 minus 3, which would be minus 1j hat, I hat rather, and then 2 minus 5, which would be minus 3j hat. So that's this vector. This is this vector. So now you've got this vector and this vector, and you can do a dot product, right? So your x, so what you end up with, the f dot, and it's a dr as well, right? You have this f dot dr that you have to do. So what is dr? You have to take the full derivative of this thing.
Isn't that 0, 0?
No, because the full, so it's not the derivative with respect to anything, it's just essentially you're breaking it up into pieces.
So it's just 3dx and 2dx.
It's actually three, let's see. I'm not remembering how that translates mathematically. How does that translate mathematically? They actually do it in the book here. I'm trying to remember. So they do it right here. Let's see. Okay, so in this example, they do this right here. And in this particular case, they actually calculate dx and dy. So dr will equal dx plus dy. But we actually have to calculate dx and dy from the line that we use. So then here's the line that we have. Here's our vector, but what is the line? This line has a slope of, so the slope is taken from the rise over around 203, right? So this equation, this one has a thing like, it looks like 2/3 x plus whatever it crosses through the y-axis, right? So where does it cross through the y-axis? At some random point, right?
That's just point slope form.
Right. So you can use the point slope form to figure it out if you want to or whatever. But once you figure this thing out, then you can actually find out what dy is. So you would find out what dy is by taking the derivative of both sides. And then you get a value for dy, and then you solve it for x and take dx. Right? So you do that. Once you do that, then you know what dy and dx are. Then you can actually do the integral. Right? So that's how you get to that, and that's what they do here. You can see here they have a function for that, so they calculate dy as this. Dy is equal to x dx, and dr is actually, I think it said it's dy plus dx, so that's not correct. It's actually dx times dy. So dr is equal, sorry, dr after you've done the dot product is equal to dx dy. Like that. So you actually have to multiply them together. And what you want to do is you want to find out a value for each of these. Then you want to do a relationship between the two, and then you want to turn everything into an x integral, and then do the integral. And that's what you can see they do that here. They turn everything into an x integral, so it ends up being x squared dx in the end.
And all you
And
have to worry about is the x's of your, excuse me, how do you know what your limits of integration are?
so the limits of integration are going to be over the path.
So that's just the x's of your
So-
previous 2 points.
So if you turn everything into an x integral, then you go from 2 to 5. If you turn everything into y integral, you go from 1 to 3. And that's the gist of it. And this example goes through that pretty well step by step on how that is done.
Yeah.
So it's just the only difference is in here they tell them the path. They tell them the path function. In this one, you have to figure it out on your own by figuring out the equation for the line. Okay. Any other questions? No problem. Were you listening for that, Patrick? Did you hear that explanation? Because we were talking about that yesterday.